And we're rolling. A video that no one will watch because everybody's here today. That's okay. You'll rewatch life?
I'll watch it.
All right. So in chapter 4, now chapter 4 is a giant chapter. There's 2 sections. That literally does it for chapter 4. So we need a quiz over both? I don't think I'm going to do that. I think I might just do one quiz out of this. And maybe, again, this is the first time I'm teaching this class, so I'm going to try to, we're going to have to make it till we make it. But I think what's going to happen in terms of, for the assessments, I'm going to do section 4142 quiz, and then I'll teach chapter 5, and maybe I'll put that stuff on chapter 5 as well. Okay, and maybe we'll do like a day of review before we do the chapter 5 test of these 2 sections of probability distributions. Now, there are more sections in chapter 4 that Stark State says, yeah, you don't need to teach those. So we are only doing 2 out of, I think, like the 5 sections of chapter 4. We're going to talk about probability distributions and binomial distributions. Okay, probability distributions and binomial distributions. Section 4.1 is probability, and section 4.2 is binomial distributions. All right, so like we do every section, we're going to start off with some definitions here. Now, what are we doing in chapter 4? Well, in chapter 2, we started with like the statistics side of this class, where we studied, all the different ways of the descriptive statistics side of it, where we said all the different ways of organizing and visualizing data in terms of pie charts and histograms and box and whisker plots and stem and leaf plots, all those different types of things. And then in chapter 3, we talked about more of the probability side of things. This is going to tie chapters 2 and 3 together, okay? Where we discuss the probability of certain statistical things happening. This is going to be more empirical probability rather than theoretical or classical probability. Okay, so we have these definitions here. When I talk about a random variable X represents a numerical value associated with each outcome of a probability experiment. A random variable. We are going to call it a discrete random variable or continuous random variable. Now, this word discrete and continuous is not just a statistics term. I talk about, actually section 2.5, for those of you in my calc class, is continuity and what it means to be continuous. Okay. And I actually talk about this with my Algebra 1 students from time to time. We talk about a discrete data versus continuous data. That does show up on the Algebra 1 OSC test from time to time. Those words, discrete and continuous. So what does discrete and continuous mean? Well, discrete means finite or countable. Finite or countable. So if I said I want to find the number of students in this class, that is a countable number, that is discrete data. If I wanted to find the number of rainy days in October, we could observe that. That's countable. Now, for continuous, a random variable is continuous if it has an uncountable number of possible outcomes. So there's, by definition, it's either countable or uncountable. What might help you is that it's represented by an interval on a number line. That's continuous. Okay, so an example of a continuous data would be like if I wanted you to find the length of time it took you to go from this class to the library. Okay. I know there is a finite endpoint, but time and temperature and length and distance, those types of things are all continuous. They're all continuous. Time, temperature, length, distance. I'm trying to think if there's any other popular examples that we use. Because there is no gaps or breaks in it. Okay. Another way you could think about it is like if you wanted to measure how tall you were, you could keep zooming in and zooming in and zooming in on a ruler. If you had a really high definition camera and if you had a really, really, really exact ruler, with a lot of lines, like an infinite amount of lines in there, and you kept zooming in at how tall you are, and zooming in and zooming in and zooming in and zooming in, couldn't you zoom in infinitely? You know, couldn't you keep going in and in and in and in and seeing, you know, infinitely how tall you are? Or think about like the temperature on any given day. Couldn't you, you know, what if it was to the nearest degree, but I wanted to go a little bit more exact, to the nearest half degree, or to the nearest tenth of a degree, or to the nearest hundredth of a degree, or to the nearest thousandth of a degree. I could keep going on and on and on and on forever like that. That is an example of a continuous random variable. All right, so let's do some examples of this. What about the number of donuts in a box? Discrete, right? Discrete. Countable, right? This would be discrete. Unless it's a baker's dozen.
Yeah.
No, it's just a dozen. Right, dozen. Yeah. You know, the book, I actually changed something. The book spelled donuts like that.
Oh, it's British.
Is that? I don't know.
I mean, it's probably British. That's not gotta be a British thing.
I changed it to donuts. I don't know. That just looks better to me. There's too many letters.
It's like color.
Color, yeah. COLOR or COLOUR.
Exactly. Color.
Color. Pounds of Jelly Bellies purchased at a bulk candy store. Continuous. Yeah, this is continuous. Good. This is continuous. Why is it continuous? Well, because I could keep, you know, I could say I wanted it to the nearest pound, but I could say I wanted it to the nearest half pound or to the nearest thousandth of a pound. You know, when you step on a scale, the scale is rounding your weight, right? It is rounding your weight. You could keep zooming in on your, you know, visually zooming in on your scale, like if it was one of those, you know, that type of scale, you know what I'm talking about. I don't know what that's called. But you could keep zooming in on your scale. You can keep getting more accurate and more accurate and more accurate with your weight. And that's a definition of something being continuous. Yes, sir.
Would it be like discrete if it asks for like specific like
yeah, if
to a whole number?
Well, I would say this. It would be discrete if I had said like I am saying I want the weight to the nearest pound of the people in this room. That would be discrete because it's countable people, and I'm rounding that answer, and there's only whole values. Right, there's only one value for it. That's discrete. But if I say pounds of Jelly Bellies purchased at a bulk candy store, okay, that's continuous. Length of time to run a marathon. Continuous. Yeah, time is also continuous. And it's continuous again because, you know, when you get a time, that's rounding it to the nearest second. But couldn't I be a little bit more exact and say, well, what's the millisecond? Or what's the, I don't know, something, nanosecond. Yeah, sure. Come on. There we go. Length of time to run a 100-meter dash. Okay, that's the same thing, right? Continuous. No, it's not discrete. Continuous. And then I got one more here. Number of points scored in a basketball game. That's discrete. Countable. There's no like 0.5 of a point. Half a period. All right. All right. So when we talk about probability distributions, and I ask you to create a probability distribution, because this will happen in the homework, which I didn't write up here yet. This will happen in the homework when I say to create a probability distribution. It lists each possible value the random variable can assume together with its probability. Okay? So I'm listing off the outcomes and then their probabilities with that outcome. Understand that this is actually, we've kind of done this already. When I asked you to provide relative frequency, that was really providing a probability distribution. We just didn't know that it was the probability distribution tag. So some things about a probability distribution. The probabilities all have to fall between 0 and 1, obviously, right? The probabilities all have to fall between 0 and 1. You can't have a probability of negative. You can't have a probability of something bigger than 1. And again, we're talking about the decimal value, not a percentage. And then the sum of the probabilities all must equal to 1. Okay, so just like relative frequency, the sum of all the relative frequencies had to add up together to get to 1. The same thing is true about the probabilities. Guys, probability is relative frequency. Probability is really relative frequency. We just didn't know probability was what it was yet. So again, when I ask you to provide a probability distribution, I'm asking you to provide the relative frequencies for each thing. So let's do that. Create the probability distribution for rolling 2 dice and adding the values together. Oh, sorry. Too fast. Too fast. Too quick. We're just really excited to do this. Yes, sir.
You going to the parade tonight?
I've got to wash my hair. Sorry. I've got to take the dog out. I've got to walk my cat.
I walk my cat sometimes.
No, you don't.
That's I do.
I tried to walk my cat.
You
couldn't handle the harness.
Yes.
No, I don't think I'm going to be able to make it tonight.
Yeah. I'll probably wear my jersey too. I'm not gonna be on the football field. I'm not gonna be on the football field.
Is there some contention?
I have to be on a different float.
Oh. What float will you be on?
The class officer float.
Oh. Well,
you believe that? I'm a class officer.
You know, you surprise me every day.
And a mentor.
No, who put you as a mentor?
That's what I'm saying.
Oh my gosh. Who's your teacher?
Miss Baker.
Okay. Does she know who you are?
No.
She trusts you. Okay, create the probability distribution for rolling 2 dice and adding the values together. So, thinking about the options here, I think this is best to show as a table. Think about the options of rolling one of them. Okay, 1, 2, 3, 4, 5, and 6. But I'm going to roll 2 of them. Okay, if I roll a 1 and a 1, what's my sum? 2. Okay, if I roll a 2 and a 1, 3, 4, 5, 6, and 7, right? All of these are the sums within there. Okay, same thing. If I roll a 2 and a 1, that's 3. 2 and a 2 is 4, and then it's just going to increase by 1. 5, 6, 7, and then 8. 3 and a 1 is 4, 5, 6, 7, 8, and then a 9. And then a 5, 6, 7, 8, 9, and 10. A 6, 7, 8, 9, 10, and 11. And then a 7, 8, 9, 10, 11, and a 12. Now, what did we create here? We created the sample space, right? This is the sample space for rolling 2 dice and adding them together. That is the sample space. So what we're going to do is we're going to find the probability of each element in the sample space. Okay, so what's the probability of rolling a 2? Rolling a sum of 2. 1 out of 36. It's a 1. 1 out of 36. Okay, so let's do this for each one. I know I got 12 sums to do. 6, 7, 8, 9, 10. Oh no.
Can we skip to the shortcut?
No. There's no shortcut.
What?
Probability 12. Okay. Well, these are pretty easy to calculate though. How many 3s do you see?
2.
2. A lot. 236. How many 4s do you see? 3. How many 5s do you see? 4. How many 6s do you see? 6. many sevens? Wait, 1, 2, 3. I only see 5. What are you talking about? Who said 6? Is that Aiden? No, it was not. 2, 3, 4, 5, 6. 36. And then it starts looping back around again, doesn't it? So I see 5 8s, 4 9s, 3 10s, 2 11s, 1 12. That is the probability distribution. Okay, so when I ask you to provide a probability distribution, I'm saying provide me the probabilities of all the different types of outcomes that I could have. Now, what's unique about this probability distribution? Like if I said to now draw a histogram from that, which I think one of the book problems has you do. If I said, okay, now draw a histogram from that, and I had it 1 through 12, well, this is 1 out of 36 all the way up to 6 out of 36, and then dropping back down again. If I actually made these bars, what would it actually turn out to be? A bell curve, a symmetrical distribution. Okay, and we'll talk about that as a normal distribution a little bit later on. Okay. I don't think I'm going to do the next problem in the notes here. It says to construct a probability distribution, and it gives you a frequency table. There is one in your homework like this, but guys, all I'm asking you to do is construct the relative frequency. Construct the relative frequency. I mean, we've done this several times before. You know, you would just say, okay, looks like I had it in my notes. This is 150, but I think it tells you within the problem anyway. We researched 150 employees. It was a personality test or something. And they had different scores on it. Well, you would say 24 out of 150, find the probability. 33 out of 150, find the probability, and so on. Okay, just relative frequencies of all these things. All right, so now let's talk about mean, variance, and standard deviation, because we could do that with pretty much everything that we covered in Chapter 2. And Chapter 4 now is connecting Chapters 3 and 2. So what does that imply about mean and variance and standard deviation? Let's talk about mean first. The mean of a discrete random variable is given by... Now, be careful with this statement here. I would like to have parentheses around that. This is without the parentheses, that's the way the book states it. So that's the way you see it on your formula sheet. But I would think it might be better to put parentheses around that so that you know what you're doing here is calculating the sum of x times p of x. You're calculating the sum of your x value, whatever your data is. Remember how many times it was. The frequency, I guess you could call it, times p of x, times the probability of that particular event happening. X times p of x. And then the actual average, the mu, is adding up all of those things. So each value of x is multiplied by its corresponding probability, and the products are all added together. So you're taking the sum of the products. The reason why I say you should put parentheses around this is some of you might be tempted to take the sum of all the x's and then multiply on p of x. Right? But there's probabilities for each little piece. So you got to multiply x times p of x for each one and then add them. I would definitely write down that your mean is actually also called your expected value. Your expected value. You know, thinking back to your Chapter 2 projects, you know, you all got your mean. That mean that we're going to be calling now is saying that's our expected value, saying if you pick the person at random, what is the value that you would expect to get? What is the value that is the highest probability? That's your expected value in for our purposes now. Okay. So let's take a look. Can we do an example real quick? Some of you are still writing. Sorry. We only got 5 minutes?
Yeah.
No homework for that.
So does that mean no homework?
No hay
Let's do the problem and then
Yeah.
homework.
No hay tarea.
But we really only have like 2. Okay.
Yeah.
Yes.
Okay. Let's do this problem and then we'll do the standard deviation and the variance tomorrow. Okay, so find the mean of the probability distribution. See, this is a nice thing about having, you know, you guys are the only class doing this because we can do that if we want. So what I'm going to look at here, I'm giving you some values of x. This has no context to it, right? This is just, the context has been taken away. This is just a table where I'm showing you x or frequency, whatever it may be, and then the probability of that thing happening. What we're going to calculate now is the mean of this probability distribution. So what I want to see is the x times p of x for each one of these. So obviously my first one would be 0.6. 5 times 0.25, okay, so that's 125. 8 times 0.4 is 3.2. 12 times 0.15, I did it already. I can just put 1.8. And then I want to sum those together. So the sum of x, p of x, I'm just going to add these together. So this is 0.6 plus 1.25 plus 3.2 plus 1.8. And that gets me 6.85. That's the mean. Yeah, that's the mean. So basically what we did here is calculated with this distribution, with these values, and knowing that this is the percentage of these likely to occur. Now notice here that it's relatively skewed left because I've got 40% chance of happening in an 8, right? 15% chance of happening all the way up to a 12, and then 45% chance of happening with a 3 or a 5, whatever this is. So the mean is obviously going to be pushed a little bit further this way, right? Because it is skewed left. So the mean is a little bit further pushed to the right. So that means here that this is 6.85. And the expected value of picking a random person within this distribution, the expected value is going to be 6.85. The expected value is mean. Mean is expected value. That make sense? Okay. We'll do standard deviation and variance tomorrow. No homework tonight. How about that? But then you will have homework tomorrow.
That's okay.
But you'll have a good amount of class time to do it. So maybe you'll get it done in class tomorrow. There you go. Yeah. Why you want to do it?
I'm okay with things. I just want to write it so like I said short periods.
Actually, I should write it. Yeah, pep rally tomorrow. Oh, I guess that's a good thing then.
So no tomorrow either.
No.
Yeah.
We'll definitely be able to finish the notes.
I can still
Let's just
go
take
for
our
it.
time. We'll see where. We'll see how.
How do I get into academic classes?
Okay. Well, I mean, I do want to do it. I think it's something to do because I don't do anything else.
So, if you ever don't work on a Wednesday
Okay.
after school, we go till 3:15.
Okay.
So we'll have practice on Wednesdays, and then we'll start doing practice. I will send you an invite through Canvas to the academic chunk business where I post updates and things like that. And then I'll get you on the reminders too. That's where I give them.
Oh yeah.
Yeah, my free time is definitely going to get more rough the closer it is to Halloween. But after that, I will
You got nothing to do.
free sailing.
Cool.
Unless I get another job, which it'll be a bit.
Gotcha.